Hello and welcome. My name is Max Peters and I'll be walking you through a poster. The poster called Time Series and Water Use Parameters. Isolate data and experimental phases to optimize evapotranspiration and a water use efficiency analysis. This poster is part of the International Plant Phenotyping Symposium 2024 held in Nebraska. Recent advances and innovation in non-destructive phenotyping methods now provide access to time series measurements. This access to time series measurements impacts the downstream options that we have in extracting water use parameters. And that's what we underline in the work presented here. We demonstrate how that time series data provides a better signal by selecting the relevant information. For instance, time series data allows us to isolate an experimental phase or to focus solely on the transpiration during the daytime. To illustrate this methodology, we've set up an experiment. In this experiment, tomato plants were grown under different drought conditions. We used the Phenospex DroughtSpotter to control and set the irrigation. In the experiment, we had three main drought conditions. So either plants were well watered in the field capacity group, some plants had a drought stress and they were kept at 60% of that field capacity, and another group was more severely drought stressed at 40% of the field capacity. Also, the experiment spanned over multiple phases. At the beginning, the plants all received the same treatment. They were all kept at field capacity. Then, for roughly a week, we gradually introduced that drought stress during a dry down phase. After that stress level was reached, we maintained that stress for about 2 weeks until the end of the experiment. But ultimately, we aim to find out if the plants grown under drought conditions are more efficient in their water use. Therefore, we used the Phenospex PlantEye to collect data about the growth of the plants. In addition, the weight data from the DroughtSpotter is transformed into an evapotranspiration signal, listing the cumulative transpiration for each plant at any given time point. But first, let us take a moment to compare the data with a more traditional approach. In traditional phenotyping, the plants would have been destructively measured for their biomass, resulting in an endpoint measurement. From the box plot, we can observe that the 40% field capacity group, they were the smallest at the end of the trial, followed by the 60% group, and ultimately the field capacity group, they were the largest in weight. In addition, traditionally, the irrigation would have been by bringing plants to a weighing station a few times a week and maybe topping them up to their target weight. At the end, one would sum up the irrigated volumes and then have the total evapotranspired volume at the end. Now, to understand which of these treatment groups make the plant more efficient in their water use, we can simply divide the total amount of biomass at the end of the trial over the total amount of water that they used. This is what that would result in, a water use efficiency box plot over the different treatments. We find the plants kept at 40% field capacity, they're the least water use efficient. Then the plants kept at field capacity and 60% field capacity, they're closer to each other, but the 60% field capacity group seems to be most efficient in its water use efficiency. However, now by having time series data, we can isolate the different experimental phases from one another. In this example, we can individually analyze the acclimatation phase for its water use efficiency. In the acclimatation phase, we can observe the plants are equally water use efficient. However, during the stress phase, there are differences in the water use efficiency. The rank is the same as with the traditional measurements. However, the differences between the treatment groups are more pronounced, since we eliminated the noise from the acclimatation and the dry down phases. So that's a great finding. The 60% field capacity group being the most efficient in their water use. However, this also gives rise to a new set of questions, such as whether the plants under drought stress, whether they transpired less. To further dive into the plant responses, we can visualize the evapotranspiration as a rate. In this example, we calculated the water loss for every hour during the trial. Since the plants do not transpire during the dark, we only focused on the daytime measurements. In the panel here on the left, we can observe the plants kept at full field capacity lost the most water during every hour, indicating these plants transpired the most. However, we also know tomato plants are classified as anisohydric, meaning they do not have tight stomatal control relative to the water potential in the soil, hence the drought stress. There is an alternative hypothesis at hand. Due to the water availability, the plants in the full field capacity treatment group could be larger. With the PlantEye data, we also have insights in the leaf area of every plant at any day. When we normalize the evapotranspiration rate, it becomes clear the plants at field capacity and the plants at 60% field capacity do not differ in their transpiration per leaf area. To sum up, the normalized evapotranspiration rate show there is no difference in transpiration per leaf area between the 60 and the full field capacity groups. This supports the hypothesis that tomato plants are anisohydric. However, the non-normalized evapotranspiration rates and the cumulative transpiration underline the plants at full field capacity did transpire more water. However, from the water use efficiency differences, we can conclude the additional transpiration did not result in biomass accumulation at the same relative rates as the 60% group. It is beyond the scope now of this research to conclude the cause, but options could include the plants at full field capacity were perhaps pot-bound or nutrient stress. Thank you for paying attention and letting me walk you through the poster. Might see you around.